Good day, I'm Norman Wildberger. In this video I'm going to introduce the idea of a group into this relatively simple geometrical context, looking at the projective line. So this is an example of an algebraic structure, somewhat an abstract one, which has a lot of applications in many different parts of mathematics. And this is a relatively simple but non-trivial, interesting example of a group that we can get our hands on. So the context is we're working in this projective line with a Euclidean structure. So it's not just the projective line, it's really the Euclidean projective line. So we're talking about lines through the origin in a two-dimensional space, determined by proportions like 3 to 1 or 1 to 2 or minus 1 to 1. We're talking about this projective quadrants, which is how we measure the separation between any two of such lines. Okay, there's two projective 1 points. This is the formula for the projective quadrants between them. And I've listed a few of them here. I should circle this one as well. Okay, so for example, the projective quadrants between these two is a half. We've seen that before. Between this line here, which is the line 1, 0, the axis line, and 3, 1 is 1/10. Just plug things in. Between here and here is 1/5. Between, say, here and here is 9/10. Between here and here is 4/5. And you can check some of those. So it's a very nice replacement or alternative to thinking about angles. I know we're all indoctrinated pretty well to think in terms of angles immediately whenever we see lines. You know, how far apart are the lines? We think about some angle. But angles are really problematic, as I've pointed out several times in this series already. And I hope you're starting to appreciate that working with angles necessitates dealing with these infinite processes which in fact don't actually end. Even to define an angle requires infinite process. You have to somehow calculate a length of an arc of a circle, which is an infinite process a la Archimedes. And then to define the cosines and sines and various circular functions and their inverses, they're all infinite processes, which in practice you really basically can never do. And so necessarily working with angles always has this approximate aspect. We're always just working with approximate values, which is highly unsatisfactory if we want to do geometry completely correctly. So this is a very important alternative to that whole story, and we'll see that it's vastly superior, both computationally and in terms of understanding mathematics more broadly. Okay? It really opens up so many other ways of thinking about things and new arenas. So we also talked about these rotations last time, these things called rows. So basically they were just symbols, rho sub A to B, and we defined this symbol by how it interacted with the symbol for a 1 point. So x to y times rho A to B is by definition this 1 point, ax minus by, to bx plus ay. And for example, if we want to, say, rotate by the minus 1 to 1 rotation, then 1, 2 times rho minus 1 to 1 is 3, 1. And so this can be viewed as something that takes this line here and gives us this line here. The same rotation acting on 3, 1 would send it to minus 2, 1, which would be over here somewhere. So it would send it to that line there. Okay, so you can check my calculations here. There's some other quadrants you might like to calculate, and you might experiment a little bit just to make sure that you understand how these rotations work and that they really do sort of behave like you would imagine rotations do. They're physically rotations, but there's no angles involved anywhere in sight. There's another important foundational issue around what I'm doing here, which I want to take a little bit of time to discuss with you. Okay, that's having to do with how we should think or interpret the symbol rho sub A to B. So we've introduced this symbol, and geometrically I've referred to it in terms of a rotation, something that's familiar to us physically. But the question is, should we really think of this thing, whatever it is, as a transformation or a mapping or a function? Typically, say, from the projective line to the projective line. So in modern 20th century usage and building up of mathematics, the functional notation for things became sort of all important. Most mathematics started being written and expressed in the language of functions, going from sets to sets. So it becomes sort of automatic for students to invoke this standard construction where you have a function, or maybe a transformation or a mapping, they all mean roughly the same thing, from one set to another set. And we think of this as being something that takes an element from this set and moves it into an element in this new set. So is that the way that we should want to think about this symbol? The answer is probably not. Okay, I don't really want to encourage you to think about things this way. There is a possibility of doing that, and we will do this informally as well. But you should recognize that that's only sort of a possible way of thinking. It's not really inherent in the actual nature of the object. So we must recognize that this thing, rho sub A to B, is actually just a symbol defined essentially by its usage in this formula. So the symbol is only defined in terms of its involvement in this formula. Now this formula, let's call it star, has many possible interpretations, none of which are essential to the meaning of this object. The meaning of this object is just encoded in this formula. The formula is the meaning. The functional interpretation is just one possible way of looking at this formula. This is a very interesting foundational point. So let's have a little bit of a more careful look at what I'm talking about here. So let's look at a specific example. So here is one of the formulas that we had a look at before, involving the projective 1.1 to 2 and also 3 to 1, and this rotation associated to the point -1 to 1. Right, so we can check that this is a valid formula. So we might ask, what does this formula mean? All right, okay, so here is one possible interpretation. Let's call it interpretation A. This formula means that the rotation rho, which is rho -1 to 1, acts on this 1 point to give this 1 point. It's telling us that we are starting with this, we're acting on this point with this rotation, and the result of that action is 3, 1. Geometrically, we're starting with this line, we're performing the rotation, and we get that line there. Okay, now here's another quite different interpretation of the same formula. Somebody else can come along and say, well, that's all well and good, but I want to think about this in a different way. That person might say, the formula means that the 1.12 acts on the rotation to give 3 to 1. So we have this rotation sitting here, and along comes the 1.1 to 2 and acts on the rotation, changes the rotation into a 1 point. That's another way of looking at what this formula is doing. There's another possible interpretation, interpretation C, which is to regard this right-hand point as essentially the mover. That we say that what's happening here is that the 1.3 to 1 joins the 1.12 and the rotation rho. In other words, this point is combining this one with this one, sort of matching up this one with this one. It's like a priest who is marrying this woman to this man. Okay? That same priest might marry a lot of other couples. This is just one particular occasion. This priest is marrying this woman to this man. That's another way of thinking about what this formula means. Well, which is right? Which is the correct interpretation? We don't need to decide this. This is not an essential part of the mathematics. All of these interpretations have some validity, or perhaps have some usefulness. In some application, it might be useful to think about this formula this way, in another application in this way, in another application in this way. The formula has an existence which is above any particular interpretation of it. Let me remind you that we are human beings, and we have a certain biology. And that biology inclines us to think in certain ways. In particular, we like to think dynamically. We like to think in terms of motion, because we live in a world in which motion plays an important role, because our biology is well suited to understanding and visualizing motion. So we have many words in mathematics that reflect this. The idea of an action of something on something else, the idea of movement, the idea of a transformation. We say that something goes to something else or is sent to. For example, we like diagrams like this. We have three objects A, B, and C over here, and two other objects R and S. And we say that, aha, here we see that A gets sent to S, B gets sent to S, O gets sent to R. We think of this as some kind of dynamic process. But mathematics does not really need to share our orientation. Okay, mathematics is something that exists in the whole universe, across galaxies, billions of years ago, billions of years from now, mathematics is there. We're just some small little planet, some ape-like creatures around for a little while. Okay, mathematics is much bigger than us. So it's not necessary for the mathematics to, be built on our particular biological prejudices and orientations. So it is far above and beyond us, mathematics is. We are privileged to kind of try to understand some little corner of it. That's great, but we shouldn't try to imagine that the thing naturally fits into our biological point of view. So the lesson that might be taken here is that functions are not necessarily so important. Functions and the functional approach to things has played a huge role in the setup of 20th century mathematics. But that might be a little bit of a red herring, or maybe a tangential direction. Because we have seen, right, that the definition of a function is in fact highly problematic. Saying precisely what a function is very, very challenging. It's usually a challenge that people don't actually address, but it's there nonetheless. Okay. So it might be that functions are not so important, that mathematics can be viewed in a more static fashion than what we're usually using. Okay. The mathematics is just there as represented by the formulas. The formulas just are there. And we can interpret them in a dynamic sense because we like to do that, but we shouldn't think that that's intrinsic to the actual nature of the formulas. Alright, so it turns out that the symmetries of our projective line with its Euclidean structure is actually more extensive than just having rotations. There are other objects around which play an equally important role ultimately. And we might call them reflections. So let's introduce reflections into the story, even though it kind of complicates things a little bit. So for any projective one point A to B, we're going to define the reflection, sigma sub A to B, as an abstract symbol satisfying this particular formula. In other words, we're going to define this symbol, sigma, purely in terms of how it interacts with a projective one point. We have a projective one point on the left, we have the symbol sigma A to B on the right, and by definition, this combination evaluates to this projective one point. And what is that? It's A times X plus B times Y to b times x minus a times y. Alright, so using projective matrices with a bit of linear algebra, the same formula can be written in terms of this product here, x to y multiplied by this particular projective 2 by 2 matrix, a, b, b minus a. So the a, b here correspond to those, and the b and minus a here correspond to the second one. Okay, so as an example, a very simple kind of calculation, let's look at a general sigma a to b acting on 1, 0. Here's our line 1, 0. What happens? Well, we have to take 1 times a plus 0 times b, that's a, and then we have to take b times 1 minus a times 0, which is b. So the effect is that this product is a to b. And what is its effect on 0 to 1? If we multiply 0 to 1 times sigma a to b, the same sigma, then we get 0 times a plus 1 times b, that's b, to b times 0 minus a times 1, so that's minus a. So we're getting this line here, b to minus a, which we've seen before a couple of times. This is actually perpendicular to a to b. It's the unique line that's perpendicular to the one that we started with. Now note, this is exactly the same as the way the rotation rho sub a to b acts on these two lines. When we multiplied 1, 0 by rho a to b, we got exactly this thing here, and when we multiplied 0, 1, we also got exactly this. So at the level of acting on the two basis lines, the rotation and the reflection seem to be indistinguishable. Well, they are indistinguishable. So to get some better intuition for what this reflection sort of does, when we're thinking about it as taking x, y, and sending it to this, let's have a look at this example here, which has a few of our familiar lines. There's 3 to 1, there is 1 to 2, and there is minus 1 to 1. There's a few other lines there too. And let's look at just the reflection associated to this line minus 1 to 1. So sigma minus 1 to 1. We're going to see what does it do to various points when we multiply by it. Okay, so we've already seen that when we multiply 1, 0 to it, we get minus 1, 1. And when we multiply 0, 1 by this sigma, we get 1, 1. Let's check that. So it's minus 1 times 0 plus 1 times 1, which is 1. And then 1 times 0 minus minus 1 times 1, which is 1. So the effect is to send this line to 1 to 1. So this green arrow here represents the effect of this rotation when we're thinking of it sort of interpretation A-wise. Alright, what about some other examples? Suppose we take minus 1, 1 and apply the reflection. So that's that line there, and we apply the reflection. You can calculate that you get 2 to 0, which is the same as 1 to 0, because we're allowed to scale these proportions as we like. In other words, this reflection sends this line back to 1, 0. It undoes what it did at this first stage. Similarly, if we apply it to 1, 1, then it undoes what it did at this stage and we get back to 0, 1. So this reflection has the property that it sends this line to this line and it sends this line to this line. It really does look like it's a reflection about some intermediate line that's sort of halfway between those two lines, whatever halfway means. And similarly, this line is sent to this one is sent to this one. It looks like it's again reflection, perhaps in a line halfway between, whatever that means. Let's look at some other examples, and I'll leave you to check my computations. That 1, 2 multiplied by sigma gives us 1 to 3. So 1, 2 is sent to 1, 3. It's just a small movement. 3 to 1 is sent to minus 1, 2. there's 3 to 1, it's sent to minus 1, 2, which is this one here. Or you could also go this way. It doesn't really matter which way we think about the movement. So in all cases, it does really look like we are reflecting, but whether we're reflecting in this line or a perpendicular line, it's a bit hard to say. It looks like they're both equivalent. And the existence of these red lines is not yet established. So the red dotted lines here appear to be the reflecting lines of this reflection, but it turns out that in fact they don't exist. Okay. So this is a reflection which is not associated to an actual reflecting line. That's just the way it is. All right, so please check these computations and make a few computations of your own, right? It's very easy. You just draw some lines and you apply the formula and you see what happens to the various reflections of various lines. You get a good sense of what these reflections do. Okay, so now we have some important exercises for you to do. Okay. So the first one is to show that this reflection sigma is indeed an isometry. The same property that the rotations that we talked about in our last video had. Namely, if we take the quadrants Q between C times sigma and D times sigma, we get the same thing as the quadrants between C and D for any two projective 1 points C and D. So we have two projective 1 points C and D, we measure the quadrants between them, that's a certain number, and then we apply a reflection to both of them, that the quadrants between the new image points is going to be the same as the original ones. And the second exercise is to establish some identities that relate reflections and rotations and the multiplications of two of them. So this follows very much this formula which we established in our last video. All right, how one rotation followed by another rotation is another rotation whose indices are obtained from the indices of these ones in some pleasant fashion that was closely connected with complex number multiplication. So I want you to extend this now to not just understand what a rotation times a rotation is, but also what a reflection times a reflection is, and what a rotation times a reflection is, and what a reflection times a rotation is. So for example, this is saying that if we rotate by A to B, and then we rotate by C to D, the effect of doing both of those is the same as a single rotation about this new point, AC plus BD to AD minus BC. And if we combine a rotation, sub A to B, with a reflection, sub C to D, then we get another reflection now, whose indices are obtained by AC plus BD and AD minus BC. And similarly, if you do it in the other way around, you do the reflection first and then the rotation, well, then you also get another reflection, but it's a little bit different from the one that you got in this case. So the situation is not commutative anymore. Okay, so we get AC minus BD here and AD plus BC. Okay, and I just want to recall that the meaning of these compositions is the following. If P is a 1 point, then sigma 1, sigma 2, that product acting on P, or multiplied by P, is by definition this. What you get when you multiply P by sigma 1 first, and then multiply by sigma 2. So basically moving the brackets from here to here. It's kind of an associative law when combining these things. Okay, so these formulas were part of my paper that I wrote some time ago called One-Dimensional Metrical Geometry. So you can have a look at that if you want some more detail. Appeared in Geometria Dedicata in 2007. And that has more information that will extend the story in other directions as well. And we'll talk a little bit about some of the other directions that, that are going on there. So we have this very pleasant situation where our projective line supports both rotations as well as reflections, rhos and sigmas. And we've seen that these things are closed under multiplication or composition. When we combine any two of them, we get another object of the same kind, either one of these or one of those. Now there's some special aspects of this situation which is very important, so from a structural point of view, associated to this word group in mathematics. Alright, so one of the aspects is that there is a special isometry called the identity. The particular rotation rho sub 1 to 0 has the property that when you take x to y and you multiply by rho 1 to 0, you get back x to y. It acts as the identity. It doesn't change the object when you multiply by it. It's like multiplying by 1 in the natural numbers. So we might say that rho 1 to 0 is e, introduce this new term e for it. Once we have this idea of an identity, we can also talk about the inverse of any of these isometries. So if we take rho a to b and we multiply by rho a to minus b, then you can check that what you get is e. Please do that. And you get the same thing if you do it in the other direction too. If you do rho a to minus b first and then a to b. So we say that these two are inverses in this group kind of structure because when we multiply them together we get 1. Just like in ordinary multiplication, say 2 and a half are inverses because when we multiply them together we get 1. Similarly with the sigmas, but the situation there is a little bit simpler because the inverse of a reflection is just itself. You do a reflection and then you do it again, multiply those two together, you can check that what you're going to get is this identity rotation. And this is a kind of common symbol that we introduced for this inverse idea. So we write rho a to b to the minus 1 up here equals rho a to minus b to reflect the fact that these two are inverses in this multiplication. And the third kind of important property is that this multiplication is associative. What does that mean? Well, it means that if we have any three isometries, say tau 1, tau 2, and tau 3, and these taus could be either rotations or reflections, then if we multiply tau 1 times tau 2 first and then by tau 3, we get the same thing as tau 1 times tau 2 times tau 3 in that order. So the brackets, where the brackets are doesn't matter. I'll leave it to you as an exercise to prove these statements. Very good exercise involving a bit of work. Okay, so now we want to formalize what's going on here with this group structure. So we're going to introduce the idea of a group in the context of this isometry situation for our simple projective line. Alright, so we're going to talk about the group structure on the isometries. So what we're going to do is we're going to define a new type of object, which we'll write perhaps like this: isom of P1Q, so the isometries of the projective line, together with this projective quadrants, which is an essential aspect of the geometry that we're building. All right, we start with a projective line. We impose this particular notion of quadrants or projective quadrants, and then we see these various notions of reflections and rotations and so on appear. Okay, and we call this the isometry group of the Euclidean projective line. Okay, and what actually is it? What does it consist of? Well, the isometry group consists of two types of objects. Objects of the form rho a to b, where a to b is a projective 1 point, and sigma, say c to d, where c to d is another projective 1 point. So these are the two kinds of objects that are going to be included in this object. So when we define, for example, rational numbers, we talked about RAT being this sort of domain which consists of things of the form A over B. Now we're considering a new kind of object which consists of not just one kind of object, but two different kinds of objects, two different kinds of symbols, which are going to be included in this group. And note that this is not a set. Right? We're not supposing that we have collected all the rotations and all the reflections together in a set, because we haven't. These numbers here can be very, very big. They can be fractions with huge numerators and denominators, perhaps, far bigger than we're able to actually put onto our computers. We're only really saying that we have a way of identifying that, yes, this object that we see in front of us is an object of this kind, or it's an object of this kind. Right? That's all we're really talking about. A way of identifying individual objects and saying, yep, we're talking about something in this object. So it's rather a specification of a type of object. The objects themselves are particular symbols. These things are just symbols, subject to the multiplication rules of exercise 138.2 that we've just talked about. Well, we have those 4 laws: how to multiply a row times a row times a sigma times a row, and a sigma times a sigma. So those 4 rules are going to be encoded in the multiplication structure of this isometry group. So we can now view this object independent of its origins as acting on the projective line. Once we have this list of multiplication rules for these rows and sigmas, we could remove all reference to the original projective line, except of course that the indices here are projective lines. But we don't actually have to think of this as being a rotation of the projective line anymore, or this as a reflection of the projective line anymore. We just think of them as symbols which are defined by those 4 rules given in by this exercise. This is a kind of an abstract group. We could write down an abstract multiplication in principle, at least if we had only a small number of reflections and rotations. All right, so this notion of a group is a very important one. This is the first group really that we're meeting, where we have a multiplication, and we have an identity, and we have inverses, and we have associativity. Those are really the 3 crucial properties that define this, make it what's called a group. Okay, so this is quite interesting, and it's sort of the basic building blocks for understanding the basic isometries of a one-dimensional projective situation. In our next video, I want to show you that you can extend these ideas to finite fields. That we can talk about geometries over a finite field, and that these reflections and these rotations make perfect sense there. And if we choose the finite field in a small way, we can actually encode and completely specify the multiplication structure that's going on here, and we can see things very explicitly. Gives us quite a different handle on investigating geometrical situations by having our main interest reflected in sort of much smaller, more manageable objects, which still encode or reflect a lot of the main properties of the original one that we're interested in over the rational numbers. So potentially very powerful tool, and I think you'll have fun seeing some sort of combinatorial finite discrete aspects to what's really fundamental Euclidean geometry. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.